Let us start with the video of with the problem for number 22 of vapor compression refrigeration system. What we have here in this problem, this data is referring to a 20-ton ice melting plant. Here, the refrigerant is ammonia. The temperature of the water entering and leaving the condenser are 20 degrees centigrade and 27 degrees centigrade. So, entering the condenser are 30 degrees centigrade and 27 degrees centigrade, and temperature of brine in the evaporator is around minus 15 degrees centigrade. Now, before entering the expansion valve, ammonia is cooled to 20 degrees centigrade, and the ammonia enters the compressor dry saturated state. Calculate for 1 ton of refrigerant the power expended, and the amount of cooling water in the condenser, and the efficiency COP of the plant itself. So, what is first of all given here? It is a refrigerant is ammonia, and it is creating a tonnage. It has a capacity of 20 ton ice, means it has the capacity of cooling 20 into 20 into 73. Just 1 second. It has right content. That is 210 kilojoule per minute itself. So 1 ton of ice, we know, is produced to make 1 ton of ice. We have to extract a amount of heat is equal to 210 kilojoule per minute. So for 20 ton, we have to multiply 210 by 20 ton itself. So much kilojoule we have to make we have to extract from the system by per minute itself to get this amount of refrigeration. Next, what is saying? The temperature of water entering and leaving the condenser are tendency of temperature 20 degrees and 27 degrees centigrade. So here condenser is cooled by some water. Condenser is cooled by water, which has temperature 20 degrees centigrade entrance and exit, it is 27 degrees centigrade. So at the outlet of the condenser, the temperature is supposed to be 27 degrees centigrade. So we can say, and there is another thing, the ammonia is cooled to 25 degrees in the expansion valve, it's 20 degrees centigrade. So there is a undercooling is there. Why? Is there. So what is this? And next is and temperature of brine in the evaporator is minus 15 degrees centigrade. So brine is creating a evaporator temperature at minus 15 degrees centigrade, which means it is the lower temperature T1 and T4 of the system is given as 15 degrees centigrade, and higher temperature is given as 15 degrees centigrade. Higher temperature is more or less given as 25 degrees centigrade, which is also given here, but it is supposed to be 27. Okay. What is given here? The enthalpy of liquid and vapor, entropy of liquid and vapor, and lower and higher temperature, and specific heat, and both liquid of the brine at different temperature, and vapor by ammonium vapor at different temperature itself. So tonnage is given 20 kiloton, that is to be multiplied by 210 kilojoule per kg. Temperature of the water is 20 degrees centigrade at the outlet of the water, I mean at the inlet of the water. So at the inlet of the water, temperature of the water 2 is 20 by 273 to 93 degree Kelvin. Temperature of the water which is leaving the evaporator which is equal to 27. 27 plus 23 is 300 degree Kelvin itself. And so T2 and T2 dash is given here as 25 degrees centigrade. So you have to follow it. So T2 dash and T3 dash is 25 degrees centigrade, is 20 plus 23, 273 degree Kelvin, by 298.98 Kelvin itself. T1, temperature at the entry, enter of the compressor, and T4, temperature at the exit of the condenser itself is given as T4 itself. It is equal to minus 15 minus 25 plus 273 is equal to 58.8 degree Kelvin itself. So now, and T3 is the temperature after the subcooling, and at the point of entering your throttling valve, throttling device or expander is 26 degrees centigrade. So this is given as 20 plus 273. It is 29 to 293 degree Kelvin itself. Now HF1, enthalpy of the fluid at the point 1 in fluid state. It is given at the point 1 means at the point of entering the compressor, means at temperature T1, the enthalpy at fluid state is given as 112.34 degree Kelvin, and at the point HF3 dash, the temperature at the point of exit of the enthalpy at the point of exit of the condenser is 3 dash itself. So enthalpy of in the fluid state at the point of 3 dash is given as at 25 degrees centigrade and 298.90 degrees Kelvin itself. So H1 is enthalpy at entrance is enthalpy at entrance itself is when we decide it is fully dry. Ammonia is fully dry at the point of entrance to compressor, that is at H1. So it is given by the vapor, enthalpy of the vapor 1426. Enthalpy of the vapor 1426.54 degree kilojoule per degree Kelvin. And H2 is the H2 dash enthalpy at the exit at the inlet of the condenser, means enthalpy at the enthalpy of the ammonia at vapor state at the entrance of the condenser, which is given as enthalpy at vapor state 1465.840 kilojoule per kg. Next comes the entropy. Entropy at the point 1 in fluid stage is given as 0.45772, and that at the point 3 means at the entrance of the expander is given as fluid 1 is given as entropy 0.45452. This is given here, and entropy at the fluid at the point 3 at the exit of the condenser, which is at high temperature, is given here at 1.142, and S1 and S2, which is S1 is equal to S2, where because compression asymptotic process as per our assumption, S1 is given as temperature at the entropy at the vapor stage at the point of entrance. At point of entrance of the compressor, which when it is on the vapor state and at low temperature, it is given as 0.452. S1 is equal to S2. Now vapor stage 0.5490. Yes, S2 at vapor stage at 0.490, and S2 dash is given as entropy at the entrance of the condenser, which is given as 590. This is equal to this. So Cp specific heat at liquid enthalpy is given as specific heat at liquid at the point 4, means it's given as 3.96 of the liquid ammonia at point 4, and specific heat of the liquid ammonia at high temperature, it's given as 0.396. 306, yes, high temperature is here. And similarly, the specific heat at the vapor of the vapor ammonia and vapor stage at the point 1 is 0.23, and that at the point at the exit at the point 2 at the time of entering the condenser is given as 208. So many things are given. All of them may not be required always. So first we have to find out what is the temperature at the exit of the exit of the compressor, which is T2 dash itself, which is T2. We know what is T2 itself, so we know entropy at the point 2 is equal to entropy at the point 2 dash plus 2.3 specific heat of the ammonia vapor at temperature say 25 degrees centigrade, which is given as 2.80 here, and log T2 dash, which we have already calculated, is temperature at the entrance of the condenser itself, which is given here as 290. We have to find out what will be the enthalpy at the point 2, or H2 we have to calculate here. We know H1, but we don't know H2 itself. The H2 will be H2 dash, which we know, plus Cp. There's a specific heat at the vapor at specific heat of the ammonia vapor state, which is given as at Cp2 dash multiplied by the rise in temperature, fall in temperature from T2 to T2 dash itself. So H2 will be H2 dash plus Cp2. So we put all these values here because we have calculated, we know and calculated here Cp2, and so that specific enthalpy at the point 2, 633.02 kilojoule per kg. And what is the enthalpy of the refrigerant at the point 3, which means the point after the supercooling of the liquid refrigerant, which is given as H3, HF3, which is HF3 dash, means enthalpy at the point 3 dash, which is given, minus specific heat of the liquid ammonia at high temperature, that is Cp3, multiplied by degree of undercooling. What is that? Means how much the temperature is reduced from at the exit to the undercooler, exit of the condenser to the undercooling itself. So T3 dash minus T3 itself. So both all these things are unknown or given to us. So we can put all these respective values and get HF3 is at 273.83 kilojoule. So the heat extracted or refrigerating effect per kg of the refrigerant is given as H1 minus H4 or H1 minus HF3. Both we have calculated HF3 as well as H1 14.26.54 270.83 11.50 and 0.67 kilojoule per kg. Now capacity of the plant is given as 20How to calculate the power? Which is the kilojoule per minute. So that is multiplied by 100, that is joule per second, divided by 6 into 20. 60 multiplied by 20 part 6.20 6.28 kilowatt per ton. Oh, power expected per ton, that is the per ton here. So this is the tonnage of the system, that is 20 ton. That power expected is 3.6 kilojoule divided by 60, means per minute, means per second, 3.65. It will be like this. Just 1 second, it is now 3 point. Hmm. 73 point, this is actually 753.65 itself. Divided by 60 means kilojoule per second, but divided by 20 means kilowatt, which is kilowatt. Divided by 20 means kilowatt per ton itself. The amount of cooling water in the condenser. So let MW, the amount of cooling water in the condenser is that. NW is carrying the enthalpy H2 minus HF3. From here, it is the enthalpy of the heat at entrance, and it is the enthalpy of heat at the exit of the supercooler or at the entry of the day itself. I mean, throttling valve itself. So you put the enthalpy itself and multiply by the refrigerant flow of refrigerant, which is equal to 49.53.6 kilojoule per minute heat extracted in condenser. Heat extracted